Yeah. So good afternoon, everyone, or good morning, depending on where you are located. Today, we are going to listen to the talk from Professor Michele Pavanello, who is a professor of physics and chemistry at the Rutgers University in Newark. So Professor Pavanello got his degree from University of Pisa in Italy and his PhD from University of Arizona, working with Rutgers Adamovitz. He later went to the He later went to the Netherlands for postdoctoral studies and is currently a professor at the Rutgers University in Newark since 2012. He's got several awards, notably the ACS Junior Faculty Awards and also NSF Career Awards, as well as presidential awards in 2018 and 2020. So today he's going to tell us about the work of molecular condensed phase. And one interesting part about this talk is that Professor Pavanello and his group are developing a lot of tools around the quantum Espresso package, which is very popular for many users on this forum. So Professor Pavanello, you can talk. The stage is yours.
Okay, well, thank you, Steve. And yeah, so I'd like to reiterate what we talked about before. Please do ask me questions during the talk. If you see a slide or if I say something that doesn't quite resonate with you, please go ahead and ask me the questions. We're all here. I'm here to introduce you to this field of subsystem density functional theory and other related methods. But I have no interest in going through the slides and you guys not really appreciating anything, which means please do ask questions. That is, there are no stupid questions, so please don't be shy. I know that students sometimes have hold back, but please don't hold back. Okay, let's get started. From this slide, I would say the take-home message is if you would like to get in touch with me, I think the best way is through Twitter. This is my Twitter handle. Go ahead and just message me on Twitter. Okay. I'd like to first acknowledge the people who have been doing the work alongside me over the years. This is a fairly recent group picture. We have a new member since this picture was taken. Actually, let's see. Yeah, just one member. And this is an old member. Alessandro graduated a few years ago, but he is still very much present and helps us. I think Steve has met him at the Quantum Multiscale School in Texas. And I'd like to also thank the funding agencies that have been allowing us to do the work that we've been doing and that you'll hear about today. And of course, thank you, Steve, for inviting me to give a talk at your institution.
Yeah.
Okay. Today, I'll tell you about, well, this talk really is about electronic structure methods and methods to tackle and to model large systems. What are large systems? I'll tell you what they are and why most methods and software are ill-equipped to model them. I'll show you that simplification, fragmentation, approximations such as Subsystem DFT are good ways to approach large systems. There are a few examples that I'll give you, such as ab initio molecular dynamics of liquids, water and fluid carbon dioxide. But then, of course, we're interested in material science as well, and that really has to deal with interfaces. For interfaces, I'll show you a fairly new method, orbital free density functional theory in density functional theory. I'll show you that that's not science fiction, can be done. Then, if we have time, we can talk about electron dynamics using subsystem DDFT as well as orbital free DDFT. So this is more or less the outline. Again, we don't have to go through the whole thing. interfaces. I'll show you a fairly new. Okay, so let's look at the real world. If you go out there and you talk to experimentalists, they will show you pictures like this. And they will ask you to either help them explain what they see in their experiments, or flat out predict what they could find if they synthesized something like this. Now, what are these systems? In this case, I give you two examples, photocatalysis and catalysis. A photocatalyst such as this one on the left, if you look at the dimensions of these nanorods, you're looking at 100 nanometers in diameter and maybe even micrometers in length. If you look at the system on the right, this is actually something we did in our lab. It's a gamma alumina nanoparticle. This has been imaged by Kelvin probe microscopy to compute the work function of these nanoparticles upon phosphorus doping. This is just a real system. How big is it? Well, it's 120 nanometers along the long direction and maybe 50 nanometers along the short direction. Well, as Steve mentioned, we would like what my group does, and many groups, including maybe many of you, you are interested in the electronic structure of these systems because that's the starting point for, predictive modeling. And the electronic structure of these systems is completely outside the feasibility of a code, even popular code like Quantum Espresso. So I'm going to define a large system as anything that scales quadratically or worse, but when a method that scales quadratically or worse cannot compute. So a system like this, if your method scales quadratically, it will take a certain time to compute one atom. It'll take, say, four times longer to compute two atoms, and so forth. Therefore, a system this big unlikely will be within the feasibility of a method that scales quadratically. So we really need linear scaling methods. Okay, well, what do we have at our disposal? What are the methods that we can use? Here, I'm just going to give you some cartoons to give you an idea. These dots here, these circles, are electrons. And you can see that these electrons are positioned in the same position in these four cartoons, but they are treated in four different ways. On the very left, here we have quantum chemistry. Quantum chemistry, electrons do interact, every pair of electrons interact, and the energy functional that one minimizes is the one down here, where you have the exact kinetic energy of the wave function computed with the wave function of the system, electronic wave function of the system, and the exact electron-electron interaction, and the interaction with the external potential. Now, this is complicated because the wave function is a complicated object, does not scale quadratically, does not scale linearly. This, in the best case, may scale like n to the 7th if you use couple cluster, single, doubles, and triples. So this method really is not what you would want to choose for approaching large systems. Then you have DFT, specifically cone-sham DFT, which is what's implemented in Quantum Espresso. What does that do? Well, it uses orbitals, cone-sham orbitals or waves. How many of them? These are, just to give you an idea, the difference between what's on the left and what's on the right between quantum chemistry and DFT is that in quantum chemistry, you really don't have a notion of orbital. But in DFT, the electron density and the wave function is based on just simple one electron functions, these orbitals. Well, that simplifies the calculation quite a bit because the kinetic energy now only depends on orbitals. Give me 1 second, I need to close one door, 1 second. Okay, apologies. So the kinetic energy depends on these orbitals, and this is a much faster, the evaluation of this kinetic energy functional is much faster compared to the one on the left. Yes. Oh, I think it's just background noise, perhaps. Okay. Then you wonder, what is the scaling of Condensed DFT? Well, if you apply quantum espresso, you will notice that it scales like the cubic of the system size. So if you double your system size, the calculation time will be 8 times, typically, right, on the perfect computer, which we don't have. Therefore, actually, the calculation takes even longer sometimes. Well, then we cannot use this method again, not even Condensed DFT for large systems. We have to move to more approximate method. Let's look at Subsystem DFT. Subsystem DFT uses Condensed DFT for groups of electrons or fragments of electrons. And then the electron density is given as the sum of the electron densities of the various fragments. Now, this is an exact method in principle, just in the same way as Condensed DFT is an exact method, provided that we know the needed energy functionals that appear in the energy expression. And the same with Subsystem DFT. If we know the energy functional that deals with the interaction between the subsystems, then the method is exact. An even more approximate method is orbital free density functional theory, which is the one on the very right. This method only considers the density as the main quantity, and the density can be written as the square of a single effective orbital. You can say, how can that be?
Sorry, Michele, I have a question.
Yes.
Sorry, for the subsystem DFT. How do you make sure that the total wave function is anti-symmetrized? Because you know when you have parts, then the total is not anti-symmetric. How do you make sure it's
this is a great question. This is a great question. So let's look back here in Condensed DFT. In Condensed DFT, you have n non-interacting fermions, and you write the wave function of those fermions using a Slater determinant that imposes this anti-symmetry, right? A relationship among the electrons.
Yeah.
In Subsystem DFT, the question now is, what happens if you consider exchange of electrons between subsystems? This should also incur into some sort of effect, because the wave function, total wave function, has to be anti-symmetric with respect to this exchange.
Yeah.
Now, this can be included directly, effectively, in the energy functional. So there is an exact relation that was derived by Hohenberg and Kohn back in the 60s that tells you that all you need is the electron density, meaning the electron density will there is a unique and invertible map between electron densities and wave function of a system. So in reality, all you need is the electron density, but then associated with that, you need to have an electron density functional that allows you to obtain the energy associated with the electron density. If you have that functional, you don't even have to worry about the anti-symmetry of the fermions, of the fermionic wave function, because it's already taken care of by this theorem, by this Hohenberg and Kohn theorem. Does that make sense? But of course, we need the functional, right? And in practice, we use approximate functional, which means in practice, we don't fully satisfy that Pauli exclusion principle. We only approximately satisfy it.
Yeah, this is fine. Yeah, thanks.
Yeah, sure. So orbital free DFT, in fact, has a similar problem that you mentioned, Omolulu, and that is that the kinetic energy is just a pure functional of the electron density. So you need to have a pretty good kinetic energy functional to make sure that that anti-symmetry, that Pauli exclusion principle is correctly accounted for. Okay, so the bottom line here is the take-home message is that rearrange of the energy functional. We rearrange the energy functional to introduce approximations, lower the computational cost, and perhaps even exploit error cancellation, as we will see. Okay, let's dive a little bit more in subsystem DFT. I'd like to kind of show you some of the details. The total density is the sum of the subsystem electron densities. This is an exact expression. Each subsystem density is given by a Kohn-Sham system, meaning it has its own orbitals and its own Kohn-Sham potential. Therefore, we can expand the densities the subsystem densities in terms of the squares of the Kohn-Sham orbitals. The energy functional is given by subsystem additive terms, just the sum I of E of rho I, where rho is the subsystem electron density, plus a correction that comes from the non-additive parts of the energy functional. And you can ask, what are these non-additive parts? Well, if you go all the way down here, this non-additive energy is just simply given by the total energy minus the additive energy. And that's given by the Coulomb interactions. Those are easy to evaluate. But in addition to the Coulomb interaction, you have two terms that are not as easy to evaluate and for which you need density functionals. The non-additive exchange correlation functional, just to give you an idea what's in there, if you have van der Waals interactions between fragments, van der Waals interaction is a non-additive correlation effect. So that would go in here in this non-additive exchange correlation. But we also have the non-additive kinetic energy. You know, whenever you have the kinetic energy, it turns out that is not subsystem additive. Whenever you have interaction between subsystems, you may have a non-additive kinetic energy functional that is not zero. Actually, this kinetic energy is strictly related to the Pauli exclusion principle problem that Omololu mentioned before. And we need pretty good functionals for this to work. So we can use, and from now on, this non-additive kinetic energy, I'm going to denote it with the acronym NAKE, NAKE. So we need good non-additive kinetic energy functionals, good NAKEs. We can use semi-local NAKEs, meaning functionals that depend on the electron density, subsystem electron density in a point R, as well as its density gradient. Or we can use fully non-local NAKEs, which are functionals that depend on subsystem electron density in point R, as well as in a different point R prime. These are much more complicated functionals. Okay, we have implemented this strategy in a couple of codes. One is the embedded quantum Espresso code. Essentially, it's quantum Espresso with subsystem DFT implemented in it, fully Fortran code. As of this year, we will no longer maintain that code, even though we just released version 2. Version 2 will be the last version of that code. You can find more on the website eqe.rutgers.edu. It works. It's a good code. It has everything that I will talk to you about today, but it's in Fortran. So recently, since 2020, we have been developing a different code called eDFT-Pi. This is an entirely Python code that still uses quantum Espresso as the Kohn-Sham engine to compute these additive energy terms, but uses a Python code to compute the non-additive energy terms and other things, including dynamics, including time-dependent DFT and so forth. So eDFT-Pi is what we are really putting all of our efforts in these days. There is a rudimentary website for this. We haven't released this code yet, but of course there is a GitLab repo that is open, and you can take a look. It works. Everything is there. Actually, it has more functionalities than EQE at the moment. Okay, let's move on. Why is this nice? Why is this so important? Subsystem DFT really can change the way you run your simulations. You know, for material science and chemistry, sometimes you have systems like this where you have layers these layers are not covalently bound with each other, such as a system like this, where in this case you have an alumina substrate, a molybdenum sulfide monolayer, and then some molecules on top. I'm sure some of you have dealt with similar systems. Well, with Subsystem DFT, you can actually map these various fragments onto your supercomputer. You can imagine you have compute nodes with many CPUs and you have many compute nodes. Well, you can exactly match or place your subsystems onto your computing architecture. And this is important because you can really save computational time and save resources in the end. How do we do this? Well, subsystems are assigned their own set of CPUs and simulation cells. You see these simulation cells are different sizes because you can use different sizes for different subsystems. You can take advantage of fast internode connectivity, but it's not vital. If you have small systems, you can fit them into single compute nodes, and then you don't have to use or leverage internode communication that much. And of course, this is suited, as I mentioned before, for non-covalently bonded fragments, mostly because this non-additive kinetic energy is not good enough to approach covalent bonds. Okay, let me move on and tell you a little bit about where we are implementing all these methods. And specifically, as I mentioned to you, the embedded quantum espresso has been alive since 2016 and has been retired in 2021. And then DFT-Pi is our main Python code to compute orbital free DFT functionals. And that is the base for eDFT-Pi, which then uses, again, only Python to connect various quantum espresso subsystems. Actually, we can use CASTEP as well to perform a subsystem DFT simulation. Okay.
Sorry, Michele, please, I have a question. Let me take you back to the previous slide. The one on, so no, the one on the distribution of the system. The next slide. Yeah, this one. So if you have a system and that's charged, then this system will interact with the other one. How do you account for that? Because then the electrostatic interaction is long range.
Yeah.
So
it's a good question. So the way we compute this, the electrostatic interactions are computed exactly. So we have one big simulation cell that is as big as your physical system. That simulation cell will be used for computing Coulomb R3 and Coulomb potentials. And you can say, well, but that's a big cell, right? If you have, say, 1 million atoms, that's a really big cell. Can you do it? And the answer is yes, we can do it, because we can change the parallelization at any time. We can define many communicators, parallel communicators, and we can say, okay, Coulomb potential, you exist on the large physical grid. This is an FFT grid that we use, and you will be assigned your own communicator, so that the Coulomb potential is fully scattered throughout the full grid. And then, of course, the trick then becomes hard to say, okay, now that you've scattered the Coulomb potential over the full grid, how do you then how do you copy it on the subsystem grids? And that's a big problem. But we solved this problem in such a way that it doesn't use much memory and can be done.
Thanks.
Yeah, sure. Because you can imagine, if you're after 1 million atoms, this can be a problem. Okay. So let me give you an example. Does this work? So here I'm going to show you the ab initio molecular dynamics of liquid water. And here in this graph is the oxygen-oxygen pair distribution function for liquid water. Several methods are featured, including the experiment. And one thing you see is that the red and blue, I guess aqua looking curves are very close to the experiment. What are they? They are subsystem DFT. Now this is I took this straight from a paper where we just show the functional for the non-additive kinetic energy, which is this revised PBE-K, where K stands for kinetic energy, for the non-additive part of the kinetic energy. And here we use 64 water molecules in a simulation cell and run the ab initio dynamics. Each water molecule is a subsystem, or 256 water molecule in a simulation cell, and we run the dynamics. You can see the values are not exactly the same, whether these curves are not exactly the same, whether you use 64 or 256, and there are many reasons for that. The electronic structure is exactly the same, but 256 water molecules behave differently dynamically because of the thermostat that we use. Okay. A larger system will need less of a thermostat compared to a small system. So water 64 thermostat does a lot of work. Water 256, the thermostat barely does any work. And so this is then reflected in the quality or in the difference of the distribution function. But they're both quite good, I must say. Then you look at the Condensed density functional theory result, which is knowingly, we know why is wrong. Water becomes almost like a glass when you use a semi-local functional for the exchange correlations such as PBE. This does not happen in subsystem DFT because there is error cancellation between the PBE exchange correlation functional and the Rev APBEK non-additive kinetic energy functional. And we can talk more about this if you'd like, but I'm going to leave it as that for now.
Sorry, Michele. So in this case, one would say the water 256 Rev APBEK is probably the more accurate one, because if you add quantum effects, then it will match the experiment. No?
Possibly, yes, possibly.
Yeah. Okay,
Yeah, possibly. I mean, this is a classical ab initio dynamics, so we don't really, you know, we're really after showing people, look, you can do this with subsystem DFT.
Okay. Yeah. Thanks.
Mm-hmm. Okay. Then we went on and decided to look at something like supercritical CO2. This is the density versus temperature phase. Now I forget the name of this. I have a little bit of a forgetting what these graphs are called, but this is where the supercritical region lies in this bluish aqua color, and the conditions that we simulate are where the star is. The critical point is this triangle here. Okay, now we pick a model system that contains 256 CO2 molecules in a simulation cell. Here for your, I'm just going to show two of the subsystem densities of two CO2 molecules or CO2 subsystems. Now, could you do this with regular quantum espresso? Perhaps, but it would be in my mind, it would be a big waste of resources. Subsystem DFT is much more efficient for this, as I'll show you in the next slide. In any case, here we show we run the simulation using subsystem DFT, Condensed PBE, but on a much smaller system size. I believe it was only 32 CO2 molecules. And then 3 experiments. You can see the 3 experiments. This again is the total radial distribution function for this system. and we superimpose what we compute. The agreement is not as good as we wish, and perhaps it has to do with the fact that we are using approximate exchange correlation and non-additive kinetic energy functional. But the point of this graph is that both Subsystem DFT and Condensed PBE miss the experiment in similar ways. You could argue that actually Subsystem DFT is a little better for the error cancellation argument that I mentioned earlier. Yeah, I guess this is all there is for this system. Take-home message, yeah, we can run really large simulations, and the accuracy is just about the same, if not better, as regular Condensed DFT. It bothers me that these non-additive functionals are not accurate enough to get the experiment exactly on top or better. So we went back to the pen and paper and said, well, can we develop better non-additive kinetic energy functionals? If you go down the ladder of the option that you have, you go from a local functional, which give you a potential that goes like the electron density to the 2/3. And I apologize here, I'm using N for electron density rather than rho in the previous slides, because when we develop these functionals, we typically publish in physics journals, and physicists love to see N as the electron density, while chemists like to see rho. So I'm going to use the two symbols interchangeably. So a local functional, which is the Thomas Fermi functional for the potential, goes like N to the 2/3. If you add a semi-local character, adding a dependency on the gradient, we use an enhancement factor like this. And I've showed you all the results that I've showed you so far use this semi-local functional. Then we went back and said, can we use non-local functionals? And these are much more complicated. We developed one, Emily Carter and her group developed another one. We implemented in EQE and EDFT-PI, and then we ran some simulations to show that actually things improve dramatically. So let me show you here a benchmark study where we benchmark our intermolecular interactions against coupled cluster, which is just about the best you can do. From this graph here, I'm going to show you three things. One is non-local subsystem DFT, which has this non-local exchange correlation functional VV10 and a non-local kinetic energy functional, which we call LMGPA. Okay, and these are the green histograms. This is a deviation against coupled cluster. And you can see this deviation is in the few kilojoules per mole, few kilojoules per mole, always 4 or less kilojoules per mole for these molecular dimers that are in the S22 dataset. This is a common dataset used for intermolecular interactions. The black lines, the black histogram is a semi-local subsystem DFT method. This is PW91 exchange correlation, PW91K non-additive kinetic energy, and you can see it's much, much worse than non-local subsystem DFT. If you look at the potential energy surfaces or curves, when you take these two fragments that are weakly bonded and make them come closer or farther away from each other, non-local subsystem DFT, which is this red line, follows coupled cluster pretty well, while the subsystem DFT that is with the semi-local functionals does not. Okay, so we think we have cured the problem of this low or not as good of a accuracy as one would wish for weakly bonded systems. Now we are 2 kcal per mole or less. So we are in a pretty good place. So good that we can do weakly bonded molecular crystals. Now, this is a really hot topic because the pharmaceutical company really depends on predictions of molecular crystal structures. If we can use subsystem DFT, cutting down timings compared to regular DFT, this is a big deal. So here I'm going to show you an example, and I guess I should tell you, I'm going to show you an example for the X23 test set. This is not the Marvel superhero X23, but it exists, as I found out with a Google search. So that was quite amusing. We're going to compute the lattice energies of these 23 different molecular crystals and compare them against the experiment. Well, these are the lines. So we put the X23 index on the x-axis and the lattice energy on the y-axis. And the black line is the experiment. The green line is semi-local Condensed DFT, which is totally off. The blue is non-local Condensed DFT, which is much more accurate, but also much more expensive. In red is non-local Subsystem DFT, which follows closely the experiment in a similar way as non-local Condensed DFT. The overall mean unsigned error is 2.6 kcal per mole. This is really good. I would say you can already do some serious screening of molecular crystals with this accuracy. You cannot distinguish the really tough molecular crystals, which have these really challenging systems with like within 10 kilojoules, you may have like 10 different polymorphs. We will not be able to attack those, but for screening purposes, this is definitely good enough as regular DFTs. Yes.
Yeah. How do the times compare?
This is the slide. So remember the CO2 system that I discussed with you before. If you take this model system, 64 CO2 molecule, 128, 256, and 512, and you compute timings of execution of a few ab initio dynamic steps, I'm giving you here 5 options: quantum espresso using PBE, quantum espresso using revised VV10, which is a non-local functional. And then I'm going to show you subsystem DFT with 3 options: non-local kinetic energy, non-local exchange correlation, local or semi-local kinetic energy, semi-local exchange correlation, and non-local kinetic energy, semi-local exchange correlation. And I think it's striking, right? You can clearly see that we essentially have a perfect scaling.
Yeah, absolutely. Yeah, that's good.
So there is, but of course you need to have a supercomputer, because if you have just a small computer, you won't be able to take full advantage of this.
Yeah.
But what's interesting about this is that the internode. Yeah, go ahead.
Yeah, but the scaling is not even linear. It's what type of scaling is that? It's like.
So for quantum espresso, the scaling is cubic.
Yeah.
For subsystem DFT, the scaling is linear, because you see, this is the time, right? So the time stays constant as you increase the processors and you increase the system size in equal matter, in equal proportion.
Okay,
so
you
it's
increase.
linear.
Okay. Yeah,
okay.
Okay.
And then you can wonder, okay, what about an even more interesting system like this? Now here we cheated a little bit. This metal is aluminum, 111 surface, and is very large. It has, I think, over several hundreds of atoms of aluminum. The trick that we use is to employ orbital free DFT for the aluminum slab, as I will tell you later, and subsystem DFT, and I guess Condensed DFT for each water molecule, and everything glued together by subsystem DFT. And then we wondered, can we go from smaller system containing 192 water molecules in this same structure, same configuration, all the way to 640 water molecules? Now for this, you need a massive supercomputer, and we go from 400 CPUs, number of cores, all the way to 1400 or 1300, I should say, number of cores. And this is the ratio of the timings, right? So now we are really looking at the parallel efficiency. So the parallel efficiency ideal would be 1. EDFT pi, which is our subsystem DFT, tapers off at around 0.6. Now, for 1400 CPUs and a system this big, this is a dream. This is a dream. If I did quantum espresso here, it would go down to zero, literally zero, or close to zero. So this is quite an impressive parallel scaling. Okay, we really want to cross this sub-nanometer time length scale. And we want to do it mostly without the need to take over an entire supercomputer. We still want to use a fairly moderate amount of computational resources. How do we do it? As I hinted just a slide before, we're going to use orbital free density functional theory for metallic subsystems and cone-sham DFT for semiconductors and molecular subsystems. We can put all of these together into one code, the eDFT code. Is this science fiction? Well, clearly it's not, because we have done it. So just to give you, to remind you what orbital free DFT is on the top right here, is a method where there is only one active orbital, just one. And of course, we need to use an approximate total kinetic energy. And as I've showed you before in the previous slide, we can use the same ones that we have for the non-additive kinetic energy. We can use those same kinetic energy functionals for this. So in all these examples, we have used non-local kinetic energy functionals. And we can approach big systems like this interface. Well, first, let me show you here on the left. We just took a block of aluminum and we made it, we increased the cell size using supercells all the way up to 1 million atoms. And we can compute the electronic structure of a block of aluminum with 1 million atoms with 30 hours of CPU times, or just one CPU. So obviously, if we parallelize this, and we have a parallel code, so we could parallelize this, we can cut down the timing down to maybe a few minutes. Okay. Can we approach semiconductors? So we can approach almost any metal, simple metal. Transition metals are still an ongoing line of research for technical reasons, which we can discuss if you'd like. For semiconductors also is an ongoing matter of research, but we can do silicon and we can do 3-5 semiconductors, gallium arsenide, for example. So this is a silicon nanoparticle that we could compute with orbital free DFT, and you can see that we can go all the way to a diameter of 16 nanometers, which is approaching, you know, a realistic system size. So orbital free can be used for some metals and some semiconductors, and we're going to use it in an embedding strategy, in a subsystem DFT strategy, to approach interfaces relevant for material science. Okay, so here is an example. Take a water molecule and put it on top of an aluminum slab. This is a typical setup for catalysis or photocatalysis or many types of simulations that people carry out in material science. Well, what we do now is to use orbital free DFT for the aluminum slab and cone-sham DFT for the water molecule, put them together using subsystem DFT, using these non-local functionals. And then we compute the binding energy between the water molecule and the aluminum slab. What we would like to see is that we get similar binding energies, whether we use this method or we use full regular quantum espresso. These are the binding energies in milli-electron volts when you have just one layer of aluminum or 2 layers or 3 layers of aluminum. And you can see quantum espresso, the binding energy is 192, 100, and 103 milli-electron volts, depending on the 3 layers, 1, 2, or 3 layers. Using this new embedding method with orbital free aluminum, we get 176 for 1 layer, 123 for 2 layers, 128 for 3 layers. It's not exactly on top, but is the window of binding energy has reduced of about 40 millielectron volts, but the trend is correct. It's correct even in a subtle way, because you see, going from 2 layers to 3 layers, Quantum Espresso's binding energies went up of about 3 millielectron volts, and so did the our method, went up by about 5. So we can reproduce the trend within a few millielectron volts. So I think this is a successful test for this system. Of course, we're going to have to do more tests to make sure that this indeed is retained for several systems and not just this particular system. But of course, now we have a method that we can take to the next level. Just to give you an idea, we can easily do 60 layers of aluminum 111, something that would be just simply impossible with a regular Quantum Espresso. And you wonder, what about the computational time? Well, you can see for yourself, Quantum Espresso is a computational time with the number of layers, aluminum layers, that shoots up and goes cubically with the number of layers. Our method, of course, just goes linearly, because the layers, the aluminum, is carried out using orbital free DFT. We can do other systems as well. We tested CO2 on aluminum, and we have a very similar behavior, both in terms of binding energies as well as computational timings. We can also move things in a horizontal direction. We can consider much wider slabs than any electronic structure method would allow you to, especially for metals. Again, using recovering a linear scaling method with the area of the slab. So I hope I've convinced you that this is indeed a method that could be very useful for anyone approaching interfaces in material science simulations. Of course, it's a new method, so we'll have to test it and make sure it works in the for as many systems as possible. All right, well, now, Steve, it's just about the hour now, so I could move on and tackle optical spectra and systems out of equilibrium, but it's really up to you guys. If you want me to talk some more, I can, or I can just go to the conclusions if you'd like.
I think personally, I would be happy to hear about that. I don't know. I mean,
I don't want to keep people, right?
Yeah, maybe the optical spectra, because we have some people that might be interested in calculating DDFT.
Okay. So maybe I go a little faster here. The bottom line is that to bring this method to tackle optical spectra and systems out of equilibrium, we have to do two things. The first, we have to develop a subsystem DDFT method. We have done it. The second is we have to develop a orbital free DDFT method. That's much more complicated. In orbital free, remember, we have a single active orbital. Single active orbital, which essentially is the square root of the density. When you go to the time domain, the single active orbital's time dependent is again the square root of the density, but then you have to also associate with it a velocity field. So you use something that looks like this wave function, also known as the Madelung wave function. And then we stick it into a essentially a Kohn-Sham TDDFT equation. But there are problems, because in the effective potential of this Hamiltonian, orbital free Hamiltonian, the effective potential contains essentially this is the Kohn-Sham Hamiltonian plus the Pauli potential. This Pauli potential is the difference between the, say, kinetic energy of the fermionic system minus the kinetic energy of a bosonic system. So this Pauli potential encodes what Omololu mentioned before, which is the Pauli exclusion principle among the fermionic electrons present in your system. Now we need a time-dependent Pauli potential. That's complicated because we don't know what that is. So we had to develop it. We can develop it in an easy way. Let me go back up here. By computing the Pauli potential that we have for the ground state and evaluate it for a time-dependent density. That's called adiabatic approximation, which is typically what is done in DFT for the exchange correlation function. This is not good enough for the Pauli potential. It's good enough for the exchange correlation, but it's not good enough for the Pauli potential. We really need a fully time-dependent Pauli potential. To do that, we had to go back to square one, develop a frequency-dependent Pauli kernel, and then from the frequency-dependent Pauli kernel, generate a current-dependent Pauli potential. So now the Pauli potential not just depends on the electron density, but it also depends on the current density. In a way, it has a notion of history of the electronic dynamics, a very short-lived history, right? Just a few, a very short period before and short period after. That's the kind of information that the current density contains. Okay, of course, we implemented all this in DFT-Pi, and we compute the optical spectra of small systems just to see if we get them right. So this is gallium arsenide 4, is a small cluster. We compute this using fully orbital free DDFT. And well, if you just do Thomas Fermi calculation, you get this red line for the optical spectrum, which is totally wrong compared to DDFT. If you include a adiabatic Pauli potential that is non-local, you get much better. If you include this current dependent correction to this potential, then you get almost the same envelope, spectral envelope as the TDDFT. Of course, we can do much bigger systems such as gallium arsenide, gallium 152 arsenide, 152 passivated by hydrogen atoms. Yeah, this is the kind of spectrum that we get for this cluster. Well, not really a cluster anymore, it really is a nanoparticle. This is the experiment. You can see we're missing a little piece here, which is the intraband transitions, DD intraband transition in gallium arsenide. We miss them because when we do orbital free TDDFT, we really only see the plasmonic response. So we see this big plasmon peak, but we don't see the intraband transitions. And of course, we can also compute things like what is the effect of the passivation and stuff like that. I have a few slides for subsystem TDDFT. Essentially, we run real-time TDDFT for the subsystems, everything in parallel. Every subsystem runs TDDFT in parallel with the other. The potentials are updated at every TDDFT step, and we can compute spectra. We can compute things like the frequency-dependent dielectric constant of water. This is what we did. We compare our result against the experiment, and of course we get red-shifted imaginary part of the dielectric constant. This is expected because in this case we are using PBE as an exchange correlation for the exchange correlation function, and we know that that leads to a red-shifted optical spectrum. Nevertheless, the comparison is quite good against the experiment. And then we can even check for things like what happens if we compute this spectrum just by including subsystem additive response as opposed to the full subsystem non-additive response in the system. And it turns out that these excitonic couplings between water molecules for the spectrum of liquid water make a big difference. And the effect of them on epsilon2 is this color-coded quantity. So that's actually a big effect, totally unexpected to me. Anyway, you can also do with the subsystem TDDFT. You can also do typical, molecule surface interactions. You can compute the optical spectra of this system, and you can determine how big is the effect of the surface onto the molecular spectrum. In this case, this is the molecular spectrum in black. The experiment is the dashed line, and on the right you see the correction to the molecular spectrum coming from the interaction with the surface. In this case, the surface is a monolayer of molybdenum sulfide for different distances of the molecule to the surface. You can see that actually the first peak of benzene is quite redshifted by the surface, not only redshifted, but also its oscillator strength is enhanced. So these are all effects that you would expect when molecules are nearby surfaces. Yeah, of course, we can run all sorts of analysis based on response functions, but I think it's good for me to close now and not go into details here, although if you guys like, I can. But one of the things we saw is that we could, going back here, we could, given the spectra, we could implement also we could trace these response functions in imaginary frequency and obtain the so-called C6 coefficients for the benzene. These are coefficients that are related to van der Waals interactions. And in fact, we could see that this surface enhances the C6 coefficients of benzene by about 5%, which is quite a bit. So there is this effect is known as a many-body dispersion effect, where molecules increase their ability to engage in many-body dispersion. I see there is a chat, maybe it's quite a while ago. Okay, I'll get to that question later. Okay, I'd like to conclude by saying that we are always developing new methods based on embedding, based on subsystem DFT and related methods, that we partner with other groups to extend these methods to tackle even more complex systems such as electrochemistry, for example. In this particular case, I'd like to point out a particularly interesting collaboration that is ongoing with a group of Oliviero Andreussi from University of North Texas. He's the author of the Environ Code, and the Francesco Paesani group from University of California, San Diego. The author of the MBX code is the most accurate force field for water based on many body expansions. So we're going to combine these methods to really get something that works for electrochemistry. This is an ongoing collaboration. We already have organized a school on quantum espresso back in August. Sorry, back in August we had a hackathon. In October we had the school. Feel free to check this website, quantummultiscale.org, to see what we're doing. And yeah, this is the last slide, and yeah, you can see for yourself the conclusions. And I'd like to thank you again for giving me this opportunity to speak to you today.
Thank you, Michele. It was a very interesting talk.
Thank you very much.
So for now, I will first open the floor to other people who may have questions about the talk. There was in particular one from Sunday in the chat about water.
Yeah, so it's a good question. Like, how do you decide how to fragment your system? Yeah, that's a good question. Well, if you are a chemist, you know how to fragment your system because you know where you can cut so that you minimize the interactions between fragments. So bottom line is you don't want to leave to the non-additive functionals to evaluate interactions that can be large. You want them to be weak. In the case of water, every water molecule is one subsystem, so that interactions between water molecules, which are weak, can be computed accurately by these approximate non-additive functionals. I hope that answers the question.
So there is Christian who raised his hand. You can unmute yourself and ask your question, Christian.
Thank you, Dr. Steve. Thank you, Professor Michele, for a nice presentation. I have two questions. The first one is, if you are taking 1 million of atoms running with subsystem method, which is taking just one CPU, it's a long time, but what about the number of nodes used for, and the number of request GPU per node used for this. It's not gaining on time and size, but losing on memories. Does it good to take a high system, a great system, than to take a small system and have all the property? This is a difference with experimental to take a small system. And the second question is to move from DDFT to EDFT-PI. Is it based on divide on subsystem, or is it a machine learning approaches?
Okay, thank you, Christian. Okay, so the first question really goes back to here. In principle, we can use accelerators such as GPUs. So you see here, you have a compute node. Well, you can attach to this compute node an accelerator, such as a GPU. Of course, your software has to allow for that. And as you know, electronic structure methods that are implemented efficiently for GPUs, yeah, there are not that many. For molecular systems, I'm aware of one, Terachem. For periodic systems, I think the jury is still out, right? We still don't know if it really works. I think Quantum Espresso has done a lot of work recently and ongoing work to extend to GPUs, and I think they're making really good progress, but it's still unclear whether that progress is portable to various architectures, whether it is, you know, a feasible method. Time-dependent DFT, even worse. To my knowledge, there is only one code out there which just came out of Lawrence Livermore National Lab. It's called the INQ. Again, the jury is out. Will that work? We'll see. So yes, in principle, you can accelerate simulations with GPUs. So in practice, you could say, well, if I have a GPU accelerated code, I can just take one CPU, attach one subsystem to one CPU, and then use a GPU for that. Absolutely, you can do that. Mind that Subsystem DFT not only reduces your computational work, but also your memory requirements. Every subsystem has a much reduced number of plane waves to deal with. That was a really complicated algorithm to write and to code, but it's there and you can use it. It's both in EQE and EDFT-PI. So the number of plane waves that each subsystem uses is like maybe 5% of the total number of plane waves of the large physical cell. Of course, it depends on system size, but just to give you an idea. Then the second question is about TDDFT. Yeah, can you repeat that question? Because I think I forgot the details.
Yes, the second question is to move from the TDDFT to EDFT-PI.
Yes.
Based
yes.
on divide or subsystem, or based on machine learning approaches?
Yeah. Okay. So to compute the time-dependent response of a system, we use time-dependent DFT, right? So for each subsystem, we use time-dependent DFT. Of course, if we have an orbital-free subsystem, then we use time-dependent orbital-free DFT. Okay. Now, if you choose a certain subdivision of fragments, a certain fragmentation configuration for the ground state, you must use the very same fragmentation for the time-dependent case. You have no choice, because that's how TDDFT works. You have to pick your ground state orbitals and then you evolve those orbitals, whether you do that in real time or in frequency domain using, Casida or Sternheimer. It doesn't matter, right? You have to start from the same ground state orbitals as your ground state calculation. So that fragmentation really happens at the ground state level. In eDFT-PI, TDDFT is done right now only in the time domain, in real-time TDDFT. We leverage the code of Davide Ceresoli for the TDDFT. This is called CE TDDFT and is the only real-time TDDFT code that works with Quantum Espresso. So we just simply git, our repository, eDFT-PI repository, has a link to the to Davide's TDDFT repository, and the two methods are essentially work together. Of course, we had to Pythonize his code, so many things had to go to the Python interface, but that was not too bad to do.
Thank you, sir. Could the code on your Git be available?
Yes, yes, the codes are fully public. Yeah.
And the Git site.
Yeah, they so if you go to, let me just give you here, I'll put it on the chat. If you go to edftpi.rutgers.edu, like I said, this is still a fairly rudimentary website, but you have essentially everything that you may want to know about eDFT-PI is here. Online, okay, sorry, let's go previous. Installation, okay, installation. You need all these requirements. Of course, you need to be well versed with Python and a bit more than just Python. If you git clone directly and then you just execute this Python pip install, it will do everything automatically, assuming that your system satisfies these requirements. Of course, if you're interested in this, we can set you up. You tell us what you want to do, and we can have a Zoom call, and my main developer, Shuasheng, can set it up for you on your machine. Now, one thing that you should know is that for Quantum Espresso, we use our own method called QEPI. QEPI is a Python version of Quantum Espresso. Now, this is a big development. If you go here, we even have a YouTube video to explain to you what it is and how it works and how to install it. This is a big effort. You can actually, with QEPI, you can do all sorts of things. You can use ASE. I don't know if you're familiar with ASE. You can use ASE to run simulations with QEPI. You have access to the wave functions during your ab initio dynamics. You can really do anything with QEPI. Now, just to have a yes, if you go to the quantum multiscale collaboration and you go to, I guess, the school materials, there are tutorials, and we have Quantum Espresso tutorials, QEPI tutorials, and eDFT-PI tutorials. So actually, let me just share this link with you. And you'll see, you can just get, and by the way, in this, you also have slides for the QEPI tutorials and slides for the eDFT-PI tutorials, slides for basics on embedding. And I believe here there are some videos with all of these tutorials also given during this school, which happened in Texas in October. You will recognize your colleague, Steve, back here. Yeah, this should be, I think this, if you're interested, you can go through this, and that should be enough for you to know what to do. But again, I'm happy to help setting it up on your machine.
Thank you very much, Professor. I think that we continue. I hope we continue the next time.
Okay. Are there more questions? on the chat. In any case, like I said before, the video will be put on the YouTube of the Institute. And there are also several resources from Professor Pavanello on the website, on his website, to learn about EQEPI, DFTPI, and other systems. And I also believe that's a good reason for you to be here in May and interact in person with the students, if possible. So if there are no more questions, I would like to thank you first, Professor Pavanello, for giving us the talk. It's always very interesting. And thank you all the participants too. Hopefully we'll be able to meet you and we have a lot more questions to ask about your methods, your code, and what you've done so far. So thank you again. Nice. And it's really a pleasure.
Yeah,
thank you very much.
Me too.
Thank you.
Yeah, thank you guys. And I appreciate that